Now that you are thoroughly familiar with the components and prime mover of a compressor package, let's move into compressor design and type. This is the second section of a 5-section module on reciprocating compressor operation. In addition to compressor design and type, this section will also cover gas flow and auxiliary systems. Compressors come in different types to accommodate different compression requirements. Now let's take a look at the most common compressor types. In an integral unit, the prime mover and the compressor are combined, sharing the same frame and crankshaft. The power cylinders are usually vertical and the compression cylinders horizontal. In another design, a V configuration is used with the power cylinders on both banks and the compression cylinders on the horizontal. In separable units, the prime mover is coupled to the compressor crankshaft. This is always done when the prime mover is an electric motor. In a horizontal balance opposed setup, there are horizontal cylinders on each side of the crankshaft. Usually the opposed cylinders are compression cylinders, but in some cases they are a combination of power and compression cylinders. The balancing of weight and forces on each side makes the compressor operate smoothly. Because horizontal balance opposed describes only the compressor cylinder setup, the compressor package itself can be integral or separable. Regardless of whether the compressor is integral or separable, the path of gas through the unit depends on the type of cylinder and whether it is a single or multi-stage compressor. A single-stage unit compresses gas from suction pressure to discharge pressure in one step, with one or more cylinders in parallel. After the gas is compressed, it is released into the discharge line, where it may go through a cooler before flowing to its final destination. Single-stage compressors can only increase gas pressure by a certain fixed amount. Factors that dictate how much a single-stage compressor can increase gas pressure include increased gas temperature, rod load, and horsepower requirements. So in order to obtain higher discharge pressures, there must be a multi-stage compressor package. In a multi-stage unit, gas is compressed from suction pressure to discharge pressure in stages. The discharged gas from the first stage of compression flows to a cooler. Before entering the second stage of compression, the gas goes through a scrubber. In the second stage, the gas pressure is further increased. This process continues until there is enough pressure for sales requirements or field applications. A reciprocating compressor, like any equipment, is designed to be operated within specified ranges. 3 critical areas are discharge temperature, rod load, and maximum working pressure. Manufacturers determine the proper discharge temperature of a compressor. Gas discharge temperature is affected by many things, including inlet gas temperature and pressure, the weight of the gas, compression ratio, and valve operation. The gas discharge temperature is normally not above 300 degrees Fahrenheit. Rod load refers to the structural limit of the compressor package. This is the maximum continuous operating force the compressor can safely withstand. Rod load is a force exerted on the piston rod, and bearings during the compression cycle. Pistons have 2 rod load factors: compression load and tension load. Compression load is the load on the piston rod as it moves toward the head of the cylinder. Tension load is the load on the piston rod as it moves toward the crank end of the cylinder. Rod load, also known as frame load, is figured by the manufacturer to ensure that the compressor does not exceed its capacity. Excessive rod load can be the result of valve failures, as well as increased or decreased cylinder pressures. Excessive rod load will cause mechanical failure, such as bent or broken connecting rods or bearing failure. To put it bluntly, excessive rod load will shut you down. Now, our final design point has to do with maximum working pressure, which is the highest discharge pressure the compressor can handle while operating continuously. The maximum working pressure provided by the manufacturer should never be exceeded, or damage to the equipment can result. All right, let's spend some time now talking about cooling systems. The purpose of the cooling system is to prevent overheating. Overheating can cause compressor damage, and that means costly repairs. In most cases, there is a single cooler used for several cooling purposes. The cooler may have multiple passages for lube oil, jacket water, and the compressed gas stream. That means the compressor and internal combustion engine can be kept from overheating by the same cooler. Smaller compressors may use air cooling to remove heat created during compression. Fins surrounding the cylinders increase the surface area and provide adequate cooling. However, this does not give sufficient cooling for most large compressors. Instead, on larger compressors, a water circulation system is used to provide compressor cooling. Pumps move water through the cylinder jackets and through the cooler. After being cooled, the water is then recirculated. Discharge gas is also piped to the cooler and cooled in an air-gas exchanger. From there, it can flow through a scrubber to the suction valve for the next stage of compression, or away from the compressor for further processing, or to a pipeline. In the prime mover, coolant is pumped through the engine, the cooler, and a lubricant cooler. Earlier, we talked about how important lubrication is to various parts of compressor operation. Lubrication systems prevent or reduce the wear of components due to friction, and these systems remove heat from the moving parts, providing longer life and less chance of damage to equipment. To stay effective, the lubricants should not be allowed to deteriorate or become contaminated. Lubricant levels, temperatures, and pressures should all be maintained within manufacturer's specifications. Generally speaking, compressor packages have two types of lubrication systems. In one system, lubricant is pumped to the bearings and then returned to the sump. In the other, very small amounts of lubricant are force-fed to high-wear areas, like the compressor cylinders, compressor packing, and prime mover cylinders. In the force-fed system, most and sometimes all the lubricant is used up during operation. It is extremely important that the person responsible for operation consistently check the oil level on the compressor, either by looking at the sight glass or the dipstick if one exists. Then be sure to add oil as needed. On the prime mover, the lubricant continually circulates through the lubrication system and will eventually deteriorate. So the lube oil must be checked and analyzed at regular intervals and changed when needed. This is similar in nature to changing the oil in your car at regular intervals. To help ensure safe operation, safety and control systems are built into the compressor package. The package is designed to shut down when a condition that is unsafe or that could damage equipment occurs. There are two kinds of control systems, electric and pneumatic. On electric control systems, these unsafe conditions signal the ignition system to ground and to shut off the fuel supply to the prime mover. With a pneumatic control system, the fuel supply to the prime mover is also shut off, stopping the compressor package. Other safety features include rupture discs and safety relief valves, which are installed in the compressor lines to relieve excess pressure. If, for example, a discharge valve were to malfunction, causing a sudden increase in pressure, the safety relief valve would open to release the gas into a vent, or flare line. A rupture disc in the same situation would simply burst to reduce pressure. Each compressor package has a control system to limit the speed and output of the unit. This system is designed to maintain a safe operating speed, ensuring a proper flow of gas through the compressor. There are several methods of controlling speed and output within the system. Your student manual contains a detailed description of these methods in Section 2. Please, be sure to study them in detail and ask questions if you do not understand these methods. Well, that brings us to the end of Section 2. It's time